Hello again. This is Math 1120 coming to you from the College YouTube page. The title of this lecture is More Rules of Probability 2, and we're going to be discussing independent events. As always, please be attentive learners while watching this video. The addition rule for disjoint events is used to compute the probability of observing an outcome in event E or event F. We now move on to describe a probability rule for computing the probability that E and F both occur. Before we can present this rule, we must discuss the idea of independent events. This is the definition. Two events, E and F, are independent if the occurrence of event E in a probability experiment does not affect the probability of event F. Similarly, two events are called dependent if the occurrence of event E in a probability experiment affects the probability of event F. Think about flipping a fair coin twice. What happens on the first toss has nothing to do with what happens on the second toss. So the first flip is independent of the outcome of the second flip. Let's look at some other examples. If you flip a coin and then roll a dice, the events obtain a head and roll a 5 are independent because the results of the coin flip do not affect the results of the die toss. Are the events earned a bachelor's degree and earn more than $100,000 per year independent? No, because knowing that an individual has a bachelor's degree affects the likelihood that the individual will earn more than $100,000 per year. Example C. Two 24-year-old drivers who live in the United States are randomly selected. The events male 1 gets in a car accident during the year and male 2 gets in a car accident during the year are independent because the males are randomly selected. This means that what happens with one of the drivers has nothing to do with what happens with the other driver. Now let's talk about disjoint events versus independent events. And events that are disjoint are not independent. Often students confuse this. Disjoint events and independent events are different concepts. Recall that two events are disjoint if they have no outcomes in common. That is, if knowing that one event occurs, we know the other one did not occur. Independence means that one event occurring does not affect the probability of the other event occurring. Therefore, knowing two events are disjoint means that the events are not independent. If you know one occurs, then you know whether the other one does not occur. Now we come to the important rule. This is called the multiplication rule for independent events. This is only true for independent events. We will have something, a more general formula that we will cover soon about dependent events. If E and F are independent events, then the probability of E and F both occurring is the probability of E times the probability of F. Here's an example. In a game of roulette, the wheel has slots numbered 0, 00, and 1 through 36. A metal ball rolls around the wheel until it falls into one of the numbered slots. What's the probability the ball will land in slot number 21 2 times in a row? Well, since there are 38 possibilities, the probability of landing on 21 is 1 out of 38. And the probability that you land on both is independent, so you take 1 over 38 times 1 over 38 is 1 over 1444, or approximately this number. And that's approximately 7 times in 10,000 trials. And here's how we came up with that idea. We can extend the multiplication rule for 3 or more independent events. So if events E1, E2, E3, all the way up to E sub n are independent events, then the probability of all of them happening is the product of the probabilities. Let's apply that to example 3. The probability that a randomly selected 24-year-old male will survive the year is 0.9986. What's the probability that 3 randomly selected, they are randomly selected, so they will be independent, males will survive? So 3, and then this asks what happens that 20 will survive. So we're going to, because these are independent events, we're going to multiply the probabilities. So the probability all 3 males survive is the product of the probabilities. We multiply these numbers and we get this. So the probability that all 3 males randomly selected survive is in excess of 99%, or 996 out of 1,000. All 20 survive, if we picked 20, is we raise that 0.9986 to the 20th power and we get this. And so there's a great probability in excess of 97% that all 20 will survive. But, in other words, in the example, if 2 of the males happen to live in the same house, not randomly selected, a house fire could kill both of them and we lose independence. Knowledge that 1 male died in a house fire might affect the probability the other died. So by randomly selecting the males, we minimize the chance that they are related in any way. We can also use independence in computing at least probabilities. Here we're computing the probability that at least 1 male out of 1,000 will die. So the probability that at least 1 male will die is 1 minus the probability that none die. So that is 1 minus the probability that none die. Now before we calculated this, and again this is 1,000, so we're raising 0.9986 to 1,000. Now we're multiplying a number less than 1 times itself 1,000 times, so we get a number very much less than 1 when we multiply all those together, and we're multiplying them because they're independent. So 1 minus this probability is 0.75. So if you randomly selected 1,000 males and you did it 1,000 times, then, and actually this is 100 males rather, 100 times you would expect that 1 to die in at least 75 of the samples. This is being said another different way. So to summarize then the rules of probability that we've covered so far, and we've done quite a bit, the probability of any event must be between 0 and 1 inclusive. So if we let E denote any event, then 0 is less than or equal to. The probability of E is less than or equal to 1. If you add up the probabilities of all outcomes, it will equal 1. If E and F are disjoint, then the probability of E or F is the probability of E plus the probability of F. If they're not disjoint, the probability of E or F is the probability of E plus the probability of F minus the probability of E and F. If E represents any event and E complement represents the complement of E, then the probability of E complement is 1 minus the probability of E. And finally, in this section, we talk about if E and F are independent events, then the probability of E and F is the probability of E times the probability of F. We will expand even more rules of probability when we talk about the case where they are not independent events, and this will be the conditional probability. I'm also launching LSA 6 here, which will be due sometime soon. It's called the birthday problem. How many randomly selected individuals would you have to assemble in a room so that the probability of a matching birthday, for example, my birthday, August 21st, is greater than 50%? And for this, please assume there are 365 days in every year. That will make it much easier. This is a problem you might want to think about quite a bit before you tackle it. In closing, now more than ever, time is precious. Each day must count. Do the math, it will make you strong. And now, more than ever, take care of yourself and of each other. We're all in this together. God bless you all.